Hey everyone. So now is scenario that we're going to look at is called competing species. Basically, what's going on is that two, and if you want to get into higher order systems or more, parties or groups, whatever you want to call it, compete for shared resources. So it could be that country A and country B are trying to compete for the same um, you know produce or let's see, minerals or uh, people that they want to attract to their country, whatever it may be. It's just two uh, competing for the same thing. And so they can be written as follows: dxdt is equal to x times some a minus bx minus cy, and then dy dt is equal to y times some d minus ey minus fx, where all a, b, c, d, e, f are real constants. And so we care about the first quadrant only for these kind of scenarios just because negative populations don't make much sense. And so the best way to really show the phase portraits and what physically all of this means is through example. And so yeah, let's just do one. Great. So the task at hand is draw the phase portrait and classify stability of the critical points. Great. As always, employ the method of your first case, second case, third case, and fourth case, and also multiply this out just so that there's less chance for error. So let's say that this first one up here is x minus x squared plus 1/2 xy, right? And then this bottom one here is 2.5 y minus 1.5 y squared plus 1. I don't know why I keep wanting to do a 4. 1/4 xy. Okay. And then obviously first thing is to find critical points. I've already done it twice. Again, all you need to do is decide, okay, our first case would be x equals 0, y equals 0. Our second case would be x equals 0, and then 2.5 minus 1.5y plus 0.25x is equal to 0. And then obviously, then the other two. And then test to see if it's algebraically possible to find solutions to that system. I'm just going to go ahead and write them down. So after doing this, the critical points that you should get are 0, 0, 0, 5/3, 1, 0, and 2, 2. So all the cases are going to work out. And this is fairly typical of competing species. You're going to get 4. And so usually it's the origin, an x-intercept, a y-intercept, and then a special point inside the first quadrant. So we have that. We have origin, we have the, what is this again? This is the y-intercept, sorry, yeah. Y-intercept, and then we have the x-intercept, and then we have our special point within the first quadrant. So, good to know. Next step after this is to get the Jacobian, right? So the Jacobian, if you want to practice with your partial derivatives, this would be a good point to probably stop the video and try calculating these on your own. But it's 1 minus 2x plus 0.5y. This bottom one over here is 0.25y. Over here it's 0.5x. And then over here it's 2.5 minus 3y plus 0.25x. And then you just plug in all your critical points into here. So let's start with the origin. The origin is going to give me 1, 0, 0, 2.5, which means that we have lambda 1 is equal to 1 and lambda 2 is equal to 2.5. And so this is clearly unstable. So the point, that was a lot of connecting. The origin is clearly unstable for the entire global nonlinear phase portrait. because of when we do this Jacobian, we clearly get an unstable critical point. I'm also going to go ahead and give you the eigenvectors, just in case you want to make the phase portrait a little bit more precise. So that's 1, 0, and then v2 is going to be 0, 1. So fairly nice eigenvectors. Same thing for, let's do 0 and 5/3. This matrix comes out to be 11/6, 0, 5/12, and then minus 5/2. Lambda 1 from here is going to be, let me draw like a line so that you don't get confused. Lambda 1 is going to equal 11/6. Lambda 2 is going to equal minus 5/2. So clearly we have a saddle, which is unstable. And I'll give you the eigenvectors as well for this one. V1 is going to equal, this one's kind of weird, 52 and 5. And then V2 is equal to 0, 1. So one easy eigenvector, one kind of weird looking eigenvector. The next one is, let's see, 1, 0. Plugging that into our Jacobian, we will get minus 1, 0, 1/2, 11/4. From here, we will get that our first eigenvalue is minus 1, our second eigenvalue is equal to 11/4. And so, again, we have a saddle. And our first eigenvector, again, I'll draw this line so we can separate these out. First eigenvector is going to be 1, 0. And then our second eigenvector is, again, the weird one, which is 2, 15. Cool. And then let's do our special point. What was it? 2, 2, right? Yeah. Is going to give me minus 2, minus 1/2, minus 3, 1 up here. And so for here, we're going to get lambda 1, and this one's kind of weird, so it's going to be equal to minus 5 plus root 3 over 2, and then lambda 2 is going to equal to minus 5 plus root 3 times quantity 5 plus root 3 over 2. And then, so if you notice, minus 5 plus root 3 is still going to be a negative number, so lambda 1 is negative, and then 5 plus root 3 is a positive number, times negative is negative. So this is going to be asymptotically stable. And, yeah, let me give you the eigenvectors. V1 is equal to 2, and then minus 1 plus root 3, and then V2 is equal to 2, and then minus 1 minus root 3. Great. And then, yeah, let me make a quick couple remarks. Typically in competing species, the origin is going to be unstable. That's fairly typical. The intercepts are either going to be stable or saddle, so in this case they're both saddles. And then the first quadrant point is almost always asymptotically stable. So keep that in mind. So now let's try to draw this phase portrait. So, phase portrait, right? Try to make it nice and big. Oh, actually, let me amend that because, again, we only care about the first quadrant. So let me actually make it like a right angle looking thing. So we have 0, 0. We have 0, 5/3, which is right here. We have, what was it, 0, 1? Or, sorry, 1, 0. So that's going to be about right here. It's going to be 1. And then we have our special point 2, 2, which is going to be about right here. Pretend that's drawn to scale. Okay. Let's see. For 0, 0, our eigenvectors. Well, first of all, for 0, 0, it was unstable, and our eigenvectors were 1, 0, 0, 1. So it's going to be unstable like that. So it'll approach all the way to those critical points. For, let's see, what was the next one? 0, 5/3. It's a saddle. So, and in the for the eigenvector for the let's say, I don't want to say this, the unstable direction, it was 0, 1, which makes sense because with respect to this, that means the y coordinate, so that means it's also going to approach it from here. And then it was unstable in the 52, 5 direction, which is, well, you can approximate as something like this. And I mean, the other way is that way, but we don't really care. The point 1, 0 was also a saddle, and it was asymptotically stable in the direction of 1, 0, which makes sense. So similar to the other intercept, it's going to be like that. And then it was unstable in the 2, 15 direction, which is something like this. Again, we don't care about that last one, or the bottom one, because it's not in the first quadrant. And then 2, 2 is asymptotically stable in all directions, right? So, and that makes sense, because this is clearly going towards here. And so what happens now is you can draw everything in between, because this is asymptotically stable. And I mean, if we want to be very precise, then the directions of the eigenvectors of this asymptotically stable point, it's like this. And so if it comes from other places, it'll do something like that. Yeah. And so you just fill everything in. It's the same as we did in chapter 3 and chapter 6. It's just you have to focus on a lot more now. But the concepts are the same. And so all these arrows are clearly going, excuse my bad drawing, but they're just going to this special point right here, 2, 2. And that's it. This is how usually competing species look like. They try to go towards a particular point which is of interest for both of them. Cool. Up next is the last section for chapter 7, which is predator-prey. And from there we move into Laplace. So, cool. See you.